Okay, let's get started. So today we keep talking about format string vulnerability, and we'll first look at a memory read example, then several memory write examples. So hopefully we can finish format string vulnerability today. So next week we start talking about return-oriented programming. So we just turn off ASLR on the server. So after the class, we're returning on again, so you can finish your homework. The first challenge we will have today is like this. This is format string number 11. Main function looks for, I think there's 2 arguments here, not 3, but whatever. So we do have print flag function available in the address space, just to make things a little bit easier for you. Because you already know you can put share code there. So because we have print flag function there, the stack doesn't need to be executable in this case. Just more code reuse. We call main function called vol_foo. Vol_foo takes the second command line argument, or for the first one, depending on your index from 0 or 1 as input. So this is a vol_foo. Clery is enabled here. So vol_foo has a clery. It has a small buffer, 20 bytes, a function pointer. Then there is a printf, the argument. And this argument is from user. So here we have a format string vulnerability because the format string is controlled by user. After that, we just print a new line. So there is a while loop. The while loop is looking for a temp file exploit. It will read that your exploit to a local buffer, and the local buffer is only 20 bytes. However, here we're reading 100 bytes. So you can easily do a buffer overflow with this one. So there are 2 vulnerabilities. Here, there's a buffer overflow. How do I get rid of this? You guys see it here? It's a little bit hard.
Difficult.
Yeah, but the slides are also online.
Okay, I'll follow those.
So, challenge here is clery is enabled. So this one you cannot easily override, right? So to override this one, you need to find the clery first. And this is different from the one we had before, the bypass clery, which we have a master process. The master process will create multiple child process, and each of them will have the same clery, and you hack one of the child process. In that case, this is just one process. And then how do you find out the clery? So you just use the format string vulnerability here, right? The format string vulnerability here will look for parameters for printf. And you will first find this pointer. Later, you will find the content of the buffer. After that, you will find the clery, the save the EDP return address. Right? So, in the first step, this one, you need to do a format string vulnerability. Exploit the format string vulnerability to look at the stack. There's information leakage there. After that, you can craft your own exploit and reuse that clery into a buffer overflow. Make sense? Should be straightforward, right? Okay, so how about I give you 10 minutes or 15 minutes to solve this one, then we move forward to arbitrary overwrite. So to find the calorie, you just need to put a format string there. Does any value look like the calorie here? We know there is a zero in the calorie, right? Like we need more. What? The slides? So here should be two, not three. That's final calorie. Try it again. It's very interesting. Final calorie. Okay. That's final calorie. Going again. The calorie is randomized, so every time you run it, but everything else will be the same. Yeah. So with one byte is zero, other bytes, other three bytes are different. Other. Yeah, so it's a random number. What anything? That one? Yes. Yeah, it's that one. Right. Yeah. Yeah, it's not more. Yeah, that one is, but I'm not sure what this is. Yeah. What I think. But I'm also using one of these.
I think these make up for saving or something. It's not terribly important. I'm trying to figure out how to automate something taking in these.
Oh, because this one is not taking input from SPD in, this takes input from command line, I mean.
Okay, yeah, thank you.
The dollar or whatever.
Yeah.
Command line. Right? Yeah, the first one. So actually the third one is already occurring. Yes, so you see, this one is already, because this value, the third value, and the 15th one, they're the same value. They're the same, right? Even though they are random, but they're the same. Right. So both of them are the curl array for different functions. Yeah, let's go back to the code. So we're at printf. Let's print out. But there is 20 bytes here. Okay, I think the compiler is doing something weird here. It may not be curl array for two functions. This is definitely a curl array value, but maybe this one is not checked. This is probably the one checked. Let's take a look. So this is the first printf, which has the format string vulnerability. And here, the format strings address is EBP minus 2C. Oh no, that's not the format strings address. That's the pointer to the format strings address. You got the format strings somewhere. Format strings on the stack. Then zeros here. There's a lot of substrate. Here we're getting the array. We put curl array in EBP minus C. So we can try this. It's reading input from water, so let's see the terminal connected together. This one. There's one. One. Example, what? Here we get the first argument. We save the argument with EDP minus 2C. That's the address of the format string, EDP minus 2C. So we get the curly array, put it at EDP minus C. Uh, yeah, I don't think you have to get that. It's probably something to the terminal. Yeah. You don't have to get that. So the added 20 by yes, I also try that. I don't think you have to get that. Anyone get a flag? No?
Right.
Yeah.
So if I'm getting a couple more, that'd be, but yeah,
Mhm.
but.
So the slash, give it forward. Yeah, say it over here. So. Yeah.
So, what I think I got is the. I thought.
Yeah. Yeah, absolutely. Okay.
Fine.
Yes.
So I'm going to translate to from X point to three.
No, it'll be you 20.
Okay,
So F3. Can we search F3? Yeah, what is the question?
I'm so bad at trying to use terminal, but I could not begin to press search.
No, search like, yeah, just, we go F that. We go F9. Go and find. So the first one is buffer. Yeah,
Okay,
yeah, so the
Okay.
first one is buffer.
so the buffer itself will be EP minus 20.
Yes,
So,
that's 32
Yeah.
bytes.
okay. So think the 32 byte buffer, then 18 of garbage.
No,
No.
to be. So the kernel rate is at EVP. Kernel rate is at EVP minus C, right? That's a kernel rate. Then the buffer is at EVP minus 21. Yes. Okay. So from here to here, so C is 12, right? This is 32. So from here to here, it's 20 bytes. So 20 bytes, then you need to accelerate. So after that, there will be 8 bytes of garbage. Then save the EVP. So there are another 12 bytes actually from this part. This is 12. This is save EVP. Yeah. Four, five. You guys get the fact? Stop bring out. Like you said.
Wondering if I'm driving the wrong thing, area is at the third. Point X or
What?
F or
What do you mean?
never mind.
So the curve is correct. I don't know what happened to the server. It worked yesterday. What's going on? Okay. Sometimes you get a stack matching, right?
I also got a stack smashing, but it was when I had something like 400 characters.
Uh, yeah, I'm not getting the stack thing here. Let's see what's going on here. Okay. So now we are here. So the buffer is at EBP minus so EBP buffer is at EBP minus the buffer. So this is both time. We have a rig somewhere. Right? So this is F rate. So the buffer is EBP minus 20.
Yeah.
Okay. And so this is the value we have on stack. That's return address. Huh? What's that? We're already over it. Not yet. So this is what the stack looks like. So buffer is 32. No, from buffer to save the EBP is 32, which is this. Okay. So this one is save the EBP. This one is return address. Okay, that's correct. So this is the return address. That's main, and we are trying to overwrite this one. And the color rate is this one. And we have the correct color rate here as well. Okay. And let's say if we successfully overwrite this, we are at here. So after F read, we should write that. say, well, several more instructions. One, two, three, four, five. 5 instructions to go. So, okay, we just did F3. So now we should examine our stack again. So this is our stack. We have the 28s there. Then we have the calorie, which looks good. 5953. Okay. Then we write this part. This is also correct. This is correct, right? This is the right address. So we keep going from here. If we get to return, we should return to we continue. Now we are at the last instruction, which is return. So now when we return, we should return to print secret, print flag. And here, we already passed the stack check. That didn't give us a smashing stack error there. So when we go here, we are in print stack. Okay, so we are here. But right now we're debugging it, so we cannot really print. Okay. I think the problem here is the print flag function. In this case, I think that's a problem. The problem you were talking about there too, the flash problem. Yeah, I think maybe the flash problem. So it's not really putting it out into the terminal, but we successfully called print flag. I think the problem is the print flag function I have here has a return. You should just give it to exit 0. Then you should flush out things. Yeah, so here it's correct. Okay, let me fix this later. But this approach should work. It's just my infrastructure has some issue there. Does that make sense? You use this approach to find the query, and is there any way we can, without changing the code, how do we get that? Yeah, we can do share code. Yeah, then we can do that. But we still have a lot of things, many other things to cover. So, okay, let me fix this. I'll repeat you guys later. Okay, so let's move forward with other arbitrary right vulnerabilities. So have we talked about this one? We did, right? This one we talked about. Oh yeah, we should go to, sorry. We should go to this one, F5. Okay. So last week, not last week, Tuesday, we talked about format string 5. And in format string 5, we were trying to overwrite the global variable auth, and it was successful. But obviously, we do not have to overwrite the global variable in this case. We can also overwrite the return address on stack. And this program actually print you the address of the return address on stack. And this piece of code is for that. We have a local variable stack, and this one holds the address of stack that we use. So this is AT&T syntax. So we're moving from the first operand to the second one. The second one is %n, the percentage 0, which is the local variable stack here. Then we're moving the content in register EDP to this local variable. And now we have what EBP points to, and EBP points to the saved EBP. So EBP plus 4 will have the return address. So that's how we get the so stack plus 4. That's our return address. Okay. Then we have a local variable 512 bytes fgets input into this local variable. There is no overflow here. However, there is a printf. That's a buffer over. So that's a format string vulnerability here. And because of that, we will be able to do a percentage n arbitrary override to, we want to overwrite this stack address. Okay. So how do we do this? Any idea? So for our temp buffer, we still want to write the address at the beginning, right? So we should have the address, which is the address of the return address right at the beginning. Okay. Now after that, we will have a lot of percentage x. Eventually, we have a percentage n here, and that percentage n should map to this. Right? Make sense? And how many bytes we're overriding? We're overriding, because we want to override the return address, we override 4 bytes. That's maybe a big number. So we can break it down to 2 bytes or even 1 byte. Right? So if we only want to override 1 byte, we use percentage n n. Okay, so that is 1 byte. H means half byte, half word. Okay. So here we probably only need to override 2 bytes because the higher 2 bytes. So what in the return address is already a code address. So the higher 2 bytes will be 08, 04, right? It will be the same. So we only need to override the lower 4 bytes. So what we need here is 2. So we have 2 of this, HHN, and in the middle, we probably need to add something to change the value. Right? First, we need to find out how many percentage X or percentage D we need at the beginning. Now after that, we can use this address. Let's take a look. For string 5. So we are solving this one using a different approach. And I don't remember how many percentage we need there. This one takes input from. So first, we know that the return address is at FFE6 AC, and we want to put that address at the very beginning of our buffer. That makes sense easier. You don't have to put it there, but that will make sense easier. E6 FF. So after that, we were putting some X. Maybe We see that value? Oh, yes. So when we print out 10 values on stack, we saw our value FF E6 HC here. So that is 1, 2, 3, 4, 5, 6, 7. That's a seventh, which means the seventh percentage X. We need to change that. So here we only need 6 of those. Then the seventh should be percentage X. But here we only want to overwrite 1 byte instead of 4 bytes. So we actually need 2 of those addresses. Right? So one for the lower byte, other one for the higher byte. We're talking about 2 bytes here. So one address is 8C, the other address is 8E. Make sense? So the seventh, we get that first address. The eighth corresponds to the other address. Right? So we need to change those two. So there'll be 6 here. After that, we will have percentage HHN. We actually need a lot of percentages. Okay. So there's a lot of tricks. Yeah, go ahead. Byte, 1 byte. Yeah, we're overriding 1 byte. So far we have been printing out. This is 8 bytes, right? This is 9 because there's a dot. So that's 54. 54, that's 62 bytes, right? 62 bytes, and the address we're writing to is 8C. Next to decimal. 8C, that's a big number. So it's 140. 140, it means we can change one of those or both of those. 140, so this is 8 bytes. But there's another thing is between this HHN and this HHN, we need to print out something number 2, right? Because of that will map to something in between. So we need to add 4 bytes here. Well, okay. And let's add 4 bytes here. So this 4 bytes, the value doesn't really matter. So here we have percentage E here, okay, like this. So this is 12 bytes. That's 12 bytes, and we are going to write 140 bytes in total, right? So we got 128 bytes. And we need 6 of those. The easiest way I can think is maybe just the 5 of those. That makes them 50. So we need 1 more. What should be the number for that? This is 20. That's 50. So we need 78. Sounds good. 78. So here we will have 78 bytes. So after that, the next byte is E6. E6, which is 214, and we already have 140. Then we need another 74 bytes. Here we have 74, right? Correct. Sorry. Okay, that's a tricky part. Is the calculation correct? Should be not, right? Buffer is 140 or rounded. Yeah, buffer is 500. Yeah, we have enough. And I think that is into the I don't have to expand it. You don't need the. Yeah, but that would be the same, right? The last one? Yes, you mean here we put A's, whatever. Yeah, but we already put it here, so I think it's just a calculation. If we change that, then we need to move here as well, right? So let's just recalculate this one. 4, 4, 4. Those are correct. 8. So here, this is 10 for sure. And 58. 58. Yeah, 58. Ooh. How much? How many are we want? We want 140, right? This is not 140. How can we get this number? How can we get this number? Yeah, it should be what? 82, right? Should be 82, we can get 140, yeah. So it should be 82 here. So if we get 82 here, the other one, we probably should get a, oh, the other one is correct. You already checked where by 140 minus 278, 78 is correct. All right. So what's the value again? The value was 8C. Oh, okay, it's 8C. 140. Yeah, so why 72? So here we have 12. Here we have 50. That's 62. Okay, that's 62. Okay. Oh, 62. Okay, so 78 here is correct. Then this one is E6. Oh, so this is too much. So this is 140 plus this. This looks correct too, huh? Wouldn't that mess up the basically like the yeah? Like that. No, this one we're looking for this value. It doesn't really matter. One. Okay, I think it's still a calculation problem, so let's give out again. Unless there's something weird going on the server today. Let's debug this to see if the calculation is correct. Maybe something weird going on the server today. The server point. Well, we get a segmentation fault. That's a good thing. Means we are. There's fault. Okay, where are we? There's a waffle. Just bring it up. So this is the first printf, second printf. We only care about the second printf. Yeah, we only care about the second printf. And it is at this place. The second printf. So set a breakpoint. And it was second printf. Then we run this program, several instructions. Now we should have the stack ready. Let's say maybe several more instructions. So if we examine the stack from EVP. Yeah. So EVP points to save the EVP, and then that's the return address. So right now the return address is this value. We are going to overwrite that using. Oh, this one, the address will also be different. Hold on. So this one address is, so here is B678. So this address will be B67C. Yeah, because in DDB the address is different. Yeah. So it should be 7C. That's an address. Run this again. Let's continue. Okay, the return address is at 7C. Okay. So now we examine so this is the return address. Before we overwrite this, now we try to overwrite, since it's just one instruction, we do that printf. Now we are here after the printf. Now we examine this again. We didn't overwrite it, right? Here. Oh, let's see. What is it? Hmm? Yeah, no, I forgot to change this one. I forgot to change this one. I only changed this one. So we did change one button. Okay. Right. So it should be 7C and 7B. Right? Yeah. So this is 93 AB. That's a correct address. We write it again. Now change to B6BC. 11 the address we want. We want it to go to print flag. That is correct. Is it? Oh. Okay, we were wrong in the beginning. We need to overwrite. We need to get the address of print flag, right? So the value, we were trying to overwrite to this address. That's wrong. That's the return address. So we need to overwrite this value to that address. 92, 30, 36. Okay. Okay, let's go back to our calculator. Yes, that
We can also return to the, like, couple of questions after, where we have to skip the. The very like,
yes, we can return to here as well. Yes, we can do that. Yeah, but let's get the calculation right here first. Get that? So
they would have to do like.
only change one byte.
From where we are.
Yeah, but hold on. So this function doesn't print out. Oh, that's why. This program doesn't print out the address of print flag. That's why I was a little bit confused. Okay, so let's try this. 38. 36, sorry. 36 is 54. Ooh, we need an overflow, I think. That's a small number. So this one has to be 54. That's the number we're trying to override. 54. So here we have 12. Here we already have another 50. So this is what we want to change, right? So this is 50. This is 62. So we already have 62 there. From here to here, we already have 62. That's right. Then this one, we want to write 54. But obviously that's smaller than 62, so we overflow it. We add 56 there. Then we get 310. Okay, does that make sense? So in total, we write 310 because we're overwriting 1 byte. So 310 actually, the last, this least significant 8 bits, we get 54. And the higher bits, they are lost. Okay? So now we have 62 here. Then we need another 200, 248. Sounds right? Okay, you need to help me do the calculation today. Okay. So after this, we have, so this is basically 54. Well, after that, we have, what is it? Print flag. 92. 92 is 146. So we have this 54. 54, right? So 146. 54. Right. I'm very slow today. What? No, it can come. Doesn't really matter. Yeah. What person?
Have a classroom.
Can you?
Yeah.
Thank you. Okay. So what? 146 and 52, 54, whatever. I don't remember. Oh, 54, yeah. Okay. So it should be 92. for that, okay? 92. Okay, finally. So we just need to do a lot of calculations there. Thank you. So your approach would also work. But the key here is you have a vulnerability that can give you arbitrary write permission here, privilege here. You can write anything you want. Then instead of writing all 4 bytes together, because that will make this part huge and may not work. When you want to write the smaller numbers, so you write byte by byte, and you may need to do integer overflow. So you be careful with the calculation here to get that. Okay. So that is format string 5. 2 approaches with you. This one is the same idea. Yeah, go ahead. Okay. Why do we need this one?
Yeah.
Because we are trying to overwrite 2 bytes, right? And each byte we need an address. We are overwriting 2 bytes, and they correspond to 2 HHN. There's another way to do it. You use a percentage HN that will write 2 bytes. Then here you only need 1 address. But that probably is also a big number. That's 9326, right? That's like, I don't know, 150 characters. So you need to output 150 characters to the terminal, which is doable, I think. Yeah. But if it's 4 bytes, then you will maybe billions of characters. I don't know if that's doable anymore.
Instead of making the A over there, you could have saved the A later between the 2 and
Here,
from there you can remove it and save it between 2.
this one.
But
Here you can put whatever here. But if you do not use percentage E or percentage X here, then we'll not need this part, right?
I can put that the padding there.
You can, yeah, but then you will be, yeah, you can do that. Yeah, that will also make sense. I think it's doable to do 2 bytes. 4 bytes, I'm not sure. We can actually try. I think 2 bytes may be doable. So 2 bytes, the size here is correct. We don't need this address. We don't need this address. Here, then we don't. So we don't need this one. We don't need this one anymore. Then the value we're trying to write is 93. Anyone remember the number? Here. Oh, 92. 36. So this is a big number. So we need to print out almost 40,000 characters there. But I think that's doable. We have a powerful machine here, so that's why. So here we have 4 bytes. Here we have 50 bytes. Yeah. 4, 50. That's 54. What's the number we have? This number. Minus 54. So this is the number we need to write. Go back here. Okay. Let's see. Oh, it actually works. It just takes We print a lot of characters. Okay. We are actually printing out almost 40,000 white space there until eventually we get it all flat. I think 4 bytes, it's hard to tell. Let's try. We may crash the server. You will not crash the server, it may crash the system. There's a program. Okay, let's say, what's the number? 0804 9236, right? This number. It's actually not that big because the first one is a 0. So it's just a million something. So this number minus 54. This is a right. Here, well, the higher 2 bytes doesn't even matter, but let's say. It'll take like 2-3 minutes. Oh, it's not that long. Less than 10 seconds. Okay. Yeah. Okay, let's go back to this. We have another 25 minutes. I don't think we can finish this today. Okay. This one, the idea is very simple. There are just 3 global variables to override, and they have different address. The program tells you the address here. But the numbers, they're huge. So if you just override the 4 bytes, it takes much longer, but I think it's doable. That takes 10 seconds. When this one is D, that's 16 or 15 times of that, right? So that's like 1 minute, 2 minutes, that's 10 seconds. So it will be like 3 minutes, something like 2.5 minutes. So maybe this one the same. Maybe you can choose to write a small one first, then go for the next one, and go for the next one. So maybe 4 minutes. You override 4 bytes. You probably take 4 minutes. Okay. But
if you do 5, it's probably way faster. Probably way faster if you do 5 instead of 20.
Yes. If you redirect this, yeah, it's probably faster. It's because the I/O there. That's why. The terminal. That's why it's slow. Yeah. All right. That's a good point. However, this is 32-bit. If it's 64 bits, it will be much slower, right? So that's why a lot of approaches write half byte, half word, 4 byte, just 1 byte. So this one will be part of your homework. Let's say if we have time to finish something more interesting here. Okay. So now we have an arbitrary write privilege. What do we want to overwrite? We want to overwrite. We still want to take full control of the computer, right? And to do that, we need to write some code pointers. And there are so many code pointers in the address space. In buffer overflow, we're only trying to take over the return address. I think we also tried to take over a global variable, a local variable, which is a code pointer. Then there are other function pointers, like the C++. Every object has a virtual table. The virtual table has many code pointers. So most the C programs you compare with GCC, they also have a .ini section. There are some library functions will be called when the program exits. So you can also hijack those. And we can also hijack the GOT section. That's the global offset table. And we actually talked about this a little bit in the background module. We talked about a technique called the lazy binding, and I showed you a demo that when you call a function twice, the first time you actually call into a stop, not really that function. The second time you call it, I think we use the printf, demonstrate that. So the idea is when a program is loaded into the memory, the interpreter, the loader, will not resolve all the references of all the library functions because the program may not use those library functions anyway. And the resolving those addresses takes time, right? So then the technique we use here is something called a lazy binding. So when the first time a library function is called, the library will look for the say library will look for the address of that library function and put that address in a table. So the second time that function is called again, we already know where it is because it's in the table. And that is done with the help of several sections. The first one is the procedure linkage table. This section is called a table, but actually there is code. It's just a very short piece of code, stops for different library functions. Then there is a global offset table, and that is actually a table with the address of each library function. So at the beginning, when you first load the program, we don't have those addresses. They're just the random numbers or zero initialized. And the first time you call that, then we will find the address of those function and put it in that table. And this global offset table is writable. Go ahead. This is it's a linker and also loader. Yeah, also loader. Loader is like runtime, linker is standard. So, like I said, the procedure linkage table, it has code. Okay? Since it's code, it doesn't have to be that section doesn't have to be writable. It's not writable, so you cannot change that. However, the global offset table, it should be writable because the C library, the loader, will change the values in that table. Because it's writable, you can also write this. The hackers can also write this, right? So we skip this part. I demoed this part at the beginning of the class. So we have the PLT section. At the PLT section, we have a stop for many functions. So let's say the function our program, the main program wants to call is the puts function. So when the first time the main function calls the puts function, it actually goes to the PLT table. And the PLT has several instructions. It will try to reference the GOT, global offset table. In global offset table, we have the address of many different functions. And it will try that. It will go to that. You will go to that table and find the address, and it say the address doesn't really make sense. It's not really a resolved address. It's not really the runtime address of puts. Okay. Then it will go to the library, and the library will populate the value to here, the real address of that puts function here. Okay. So the second time you call puts again, it says, oh, this entry is valid. I will directly go to puts. Okay. We now need to go through the library to populate this again. Because of that, this table is writable. So this is the program we are trying to hack. Stack query is enabled here. Non-executable stack is enabled here, which means we cannot inject the shellcode to the stack to run that. However, we do have print flag in the address space. So your goal is to call or return to print flag. So next week, after you learn return-oriented programming, we can even take out this condition. Okay? You don't even need this print flag in the address space. You will just use some random bytes in the address space and glue them together, and they become print flag. Yes. So the program, very simple. We have a buffer, 200 bytes. Very convenient. We print out the printed flag address for you. Then there is fgets. Take input from std in and 198 bytes. So to the buffer, so no buffer overflow. Even if we can do buffer overflow here, it's not going to help. You need to bypass canary and the stack is not active. Then we have a printf. So this is the format string vulnerability, right? After printf, there is exit. It calls exit. Eventually this becomes a system call and call exit, right? Okay, so how do we hack this one? So in the example we just saw, we try to overwrite the return address on stack. Okay. But for that one, we know where the return address is. For this one, we don't. Okay. We don't want to brute force that. Now, how do we hack this? What's the easier way to hack this? Use what I just talked about, the lazy binder. Okay. Exactly. So printf, fgets, exit, they are all C library functions, right? They should have their address in that global offset table. We overwrite that address. So after printf, we have already overwrite the exited address in GOT. Then when the program calls exit, it's not going to really call exit. It will call our print flag. So the approach we use is first we find out in that global offset table, which entry is the address of exit. Yeah, one way to do that is use the obj dump -r. R is for global offset table. Then here you can see there are many entries here for this program. Take a look. And well, so we see printf here, gets here, exits, and each of them is 4 bytes. See, so this is actually a table. Each entry is the runtime address of this function. Try this one, please. So then we know where to override. This is the address we want to override. We also know where do we want to override to, because we have print flags address, but that's easy to get anyway. We do an nm, we probably can get that. So yeah, when we do an nm, we can also get the address of print flag. So it's not necessary to print it out. Let's say 15 minutes. It's actually the same approach. Let's say take input from std in this one. We put the address we want to overwrite at the beginning, which is excellent. This one. Forward. C0. Report. Okay. After that, we should have multiple percentage X. So first- oh, okay. Yeah, let me add a 0 at the beginning so it looks better. Now it looks better. The white space. We will find our first here. This one, right? The ninth one. So we need the ninth one, so we need to go 7 here. Everything over there. Here we have another. We also only need to override 2 bytes in this case. So HN enough. So we're writing to print flag address. This is print flag address. That's the same address, right? I think the same one. Or this is 4 bytes. Here is 70. That's 74. Only need this number minus 74. Okay, should work. Okay. Oh, works. Okay. So here we're overwriting the global offset table. And we're overwriting the entry for exit because we know that exit will be called. If you overwrite other entry, it may not work. Let's say we override fgets. We know where fgets is. Oh, fgets is here. This is our 30. Okay. So what will happen if we do this? Nothing, right? We do not even get a segmentation fault because that function is not called anymore. Yeah. Cool. That's all about the format string variability. Very powerful. Go ahead.
Not very, what is the package? Instead of saying that to already put it out the.
Yes. Good point. So,
Someone.
for those ones, they do not necessarily need that GOT table or that GOT table needs to be writable, right? In those cases, you look for other places. There is always a hole somewhere. Yes. Okay. That's actually related to the defense I'm going to talk about. So a related defense is called reload, and it has been deployed in most of our programs. When we compare that, we use reload. Even the program we just hacked, it also use reload, but you only use this partial reload. And it's not really working. We have another version of this program on the server, which is the reload version, which is a full reload version. And that program, the difference is the GOT table is not writable. Okay. I don't have time to, today we don't have time to debug that. Next week I can show you. So then when you try to write to that GOT table, you get a segmentation fault, basically. Yeah. The partial reload will still make the GOT table, especially the most important part, writable. It will make other parts surrounding it not writable. So if you do a buffer overflow, try to sequentially overwrite that, it doesn't work. But if you have a powerful tool like format string, you can still overwrite that. Yeah, and that's why it still works. I have a little bit explanation here. Besides that GOT table, like I said, there are many other function pointers in the address space you can override. There are constructors, destructors, or elite or Philly sections. In the server, on the server we have, all the applications we have on the server, we don't really have the destructor or constructor sections. They're kind of a little bit old, obsolete. But we do have the elite and the Philly section. I think you saw that. So in those sections, we even have functions like .Philly function, and there's a pointer for that. We can override that as well. So then our program, our function will be called before the program actually exits. Also, I want to mention that if you have time, read this paper. This paper, this is published like maybe 10 years ago. This paper, in a very small section of this paper, they talked about that the printf is actually Turing complete. By just exploiting printf, just exploiting the format strings, you can make it Turing complete. I don't really remember how it works. I do not have, I didn't design any challenges for that part, but I remember that conclusion there. Yes. Yes. Okay, that's it for format string. You were also changing, but the thing is, ASLR is first of all 32-bit. The entropy is not enough. But, there are many ways you can still bypass it, especially through information leakage. We did a challenge yesterday to exploit a bug there, but utilizing information leakage, you can infer where those addresses are. The entropy is not that big. 64-bit entropy is much bigger. But they slow down the attack. In one of the slides I had is called direct defense or indirect defense, right? None of them is direct defense. They're just trying to slow down the attack, but you always find a way to bypass it. And also, I think I mentioned that, especially for embedded systems, it's really hard to implement ASLR. Everything lives in the physical address space. Yeah, that's why we also need other approaches. That's why we have defenses at each layer, at a compiler layer, at OS layer, and all of them combined. Sometimes they still do not work. Okay, so next week we will talk about very exciting topic, return-oriented programming. Very exciting topic. So some of you probably already heard about that. Did any of you do any ROP before? Eric, did you do any ROP before? Once, okay. How about Dream? Did you? I heard about it. Okay, yeah. So, yeah, ROP will be very exciting because so far we have so many constraints. We try to inject the code into a address space, then they do not need us to execute that. Then we try to reuse existing code in the address space, like print flag, right? Like system, libc, So now we're just going to use some random bytes in the memory and build meaningful programs using random bytes. And that's very difficult to stop anymore because you just give me some randomly generated garbage, then we can find the meaningful instructions there, chain them together and make it to do whatever we want during compute. Cool, see you next week.